To address a high leg voltage in a 120/240 delta system, especially when feeding a 200 amp panel from a 400 amp service, a systematic approach is required. Firstly, determine the voltage imbalance. Measure the voltage between each leg and the neutral connection. In a balanced 120/240 volt delta system, the average voltage of the three legs should be approximately 120 volts. The high leg, however, will exhibit a significantly higher voltage than the other two legs relative to the neutral. This voltage is typically around 208 volts. Secondly, identify the cause of the imbalance. The most common cause is unbalanced loads, such as heavy single-phase devices connected predominantly to one phase, or worse, specifically the high leg. Inspect all wiring for open neutrals or loose connections, as these can exacerbate voltage imbalances. A faulty neutral connection can cause erratic voltage readings and increase the voltage on the high leg. Thirdly, reconnect loads or adjust wiring to better balance the system. Redistribute unbalanced loads to reduce the current flowing through the high leg. This may involve moving single-phase loads from one phase to another to achieve a more even distribution across all three phases. Check and tighten all neutral connections to ensure a solid, low-resistance path for the return current. If feasible, rewire the system to balance the loads on each phase. This may involve rerouting circuits or adding new circuits to distribute the load more evenly. Fourthly, consider installing a buck-boost transformer as an option. If the voltage imbalance cannot be corrected through other means, a buck-boost transformer can be installed. This transformer is specifically designed to reduce the voltage on the high leg by boosting the voltage on the other two legs, thereby bringing the system closer to a balanced state. Given the specific situation of feeding a 200 amp panel from a 400 amp service, there is likely an unbalanced load contributing to the high leg voltage. Examine the loads connected to the 200 amp panel with particular attention to the air conditioning unit to determine if it is a significant factor in the imbalance. If the air conditioning unit is connected to the high leg, strongly consider moving it to a different phase or upgrading it to a three-phase unit, as this can significantly reduce the load in the high leg. The following additional considerations are important. Firstly, ensure that the electrical system can handle the reduced high leg voltage. A buck-boost transformer, for example, may affect the voltage regulation of the system. Secondly, check for any potential code violations or safety hazards. Any modifications to the electrical system must comply with local and national electrical codes. Thirdly, consult with a qualified electrician for proper installation and verification. An electrician can perform load calculations, verify the wiring, and ensure the system operates safely and efficiently. When dealing with a 120/240 volt delta high leg system, it is essential to understand the potential issues and the proper methods for mitigating them. The high leg, also known as the stinger leg or wild leg, is a characteristic of the delta configuration and can present challenges if not properly managed. The voltage from the high leg to neutral is typically around 208 volts, which is significantly higher than the 120 volts found on the other two legs. This voltage difference can create imbalances and potential hazards if not properly addressed. One of the primary concerns with a high leg system is the potential for unbalanced loads. If a disproportionate amount of single-phase loads are connected to the high leg, it can result in excessive current flow and voltage drops, leading to overheating, equipment failure, and other problems. To minimize these issues, it is crucial to balance the load across all three phases as evenly as possible. This involves carefully distributing the connected devices and appliances to ensure that each phase carries a similar amount of current. In addition to load balancing, proper wiring and connections are essential for maintaining a stable and safe electrical system. Loose connections, corroded terminals, and damaged wiring can all contribute to voltage imbalances and increase the risk of electrical hazards. Regular inspections and maintenance are necessary to identify and address any potential problems before they escalate. Another important consideration is the use of appropriate overcurrent protection devices. Circuit breakers and fuses must be properly sized to protect the wiring and equipment from overloads and short circuits. It is essential to consult with a qualified electrician to determine the correct size and type of overcurrent protection devices for each circuit. In some cases, it may be necessary to install a buck-boost transformer to reduce the voltage on the high leg. These transformers are designed to lower the voltage on one or more phases, bringing them closer to the desired level. Buck-boost transformers can be particularly useful in situations where it is difficult or impossible to balance the loads effectively. However, it is important to note that the installation of a buck-boost transformer should be performed by a qualified electrician, as it involves complex wiring and adjustments. Another aspect to consider is the grounding of the electrical system. Proper grounding is essential for safety and helps to prevent electrical shocks and other hazards. The grounding system should be regularly inspected and tested to ensure that it is functioning correctly. In addition to the technical aspects of managing a high-leg system, it is also important to educate users about the potential hazards and limitations. Users should be informed about the voltage difference between the high leg and the other phases, and they should be instructed to avoid connecting sensitive electronic equipment to the high leg. Signage can be used to clearly identify the high leg and warn users about the potential risks. The National Electrical Code, or NEC, provides detailed guidelines and requirements for electrical installations, including those involving high leg systems. It is crucial to comply with all applicable NEC regulations to ensure the safety and reliability of the electrical system. Some specific NEC sections that are relevant to high-leg systems include Article 215, which covers feeders, Article 220, which covers branch circuit, feeder, and service calculations, and Article 250, which covers grounding and bonding. Article 310.15 addresses ampacity of conductors. These sections provide guidance on conductor sizing, overcurrent protection, and grounding requirements. In addition to the NEC, local electrical codes may also apply. It is important to consult with the local authorities to determine the specific requirements for electrical installations in your area. When working with a high-leg system, it is essential to take precautions to protect yourself from electrical shock and other hazards. Always to energize the circuit before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electricity, it is best to hire a qualified electrician to perform the work. In summary, managing a 120/240 volt delta high-leg system requires a thorough understanding of the potential issues and the proper methods for mitigating them. Balancing the loads, ensuring proper wiring and connections, using appropriate overcurrent protection devices, and grounding the system are all essential for maintaining a safe and reliable electrical system. Consulting with a qualified electrician and complying with all applicable codes and regulations are also crucial. Firstly, start by measuring the voltage at various points in the system, including at the service entrance, the main panel, and individual branch circuits. Use a calibrated voltmeter to obtain accurate readings between each phase and neutral, as well as between phase to phase. Record these measurements for further analysis. Secondly, calculate the voltage imbalance. Determine the average voltage of the three phases and then calculate the percentage deviation of each phase voltage from the average. A significant deviation, typically more than 3%, indicates a substantial imbalance. Thirdly, identify the sources of unbalanced loads. Inspect the connected loads to identify any single-phase devices or equipment that may be drawing excessive current from one phase. Pay particular attention to large appliances, motors, and lighting systems. Use a clamp-on ammeter to measure the current flowing through each phase conductor and compare the readings. Fourthly, redistribute the loads to balance the current. Based on the identified unbalanced loads, we arrange the connections to distribute the current more evenly across all three phases. This may involve moving circuits from one phase to another or adding new circuits to balance the load. We measure the current and voltage after the redistribution to verify the effectiveness of the changes. Fifthly, check and tighten all electrical connections. Loose or corroded connections can contribute to voltage imbalances and increase the risk of electrical faults. Inspect all connections at the service entrance, main panel, branch circuits, and equipment terminals. Tighten any loose connections and clean any corroded surfaces. Sixthly, verify the neutral conductor integrity. A properly sized and connected neutral conductor is essential for carrying unbalanced currents. Ensure that the neutral conductor is adequately sized for the expected load and that it is securely connected at all termination points. Check for any signs of damage or corrosion on the neutral conductor. Seventhly, consider using a buck-boost transformer to correct voltage imbalances. A buck-boost transformer can be installed to adjust the voltage on one or more phases, bringing them closer to the desired level. This can be particularly useful in situations where it is difficult to balance the loads effectively. Consult with a qualified electrician to determine the appropriate size and configuration of the buck-boost transformer. Eighthly, implement power factor correction. Low power factor can contribute to voltage drops and current imbalances. Consider installing power factor correction capacitors to improve the power factor of the system. This can help to reduce current flow and improve voltage regulation. Ninthly, regularly monitor the system for imbalances. Use a power quality analyzer to monitor the voltage, current, and power factor of the system over time. This can help to identify any developing imbalances and allow for timely corrective action. Tenthly, consult with a qualified electrical engineer or contractor. If you are unsure about any aspect of managing a high-leg delta system, seek professional assistance from a qualified electrical engineer or contractor. They can provide expert guidance and ensure that the system is installed and maintained in accordance with applicable codes and standards. When dealing with a 120/240 volt delta high-leg system, there are several key aspects to consider to ensure safe and efficient operation. Firstly, understanding the system configuration is crucial. A 120/240 volt delta system typically has 3 phases, with 2 phases providing 120 volts to neutral and the third phase, the high leg, providing approximately 208 volts to neutral. This high leg is often marked with orange tape to indicate its higher voltage. Secondly, load balancing is essential to prevent voltage imbalances and overheating. Single-phase loads should be distributed as evenly as possible across the 3 phases to minimize current flow in the neutral conductor and maintain a stable voltage on all phases. Thirdly, grounding is critical for safety. The system should be properly grounded to provide a low impedance path for fault currents, reducing the risk of electrical shock. The grounding electrode conductor should be sized according to the National Electrical Code, or NEC, and connected to a grounding electrode system. Fourthly, overcurrent protection devices, such as circuit breakers and fuses, should be properly sized and installed to protect the wiring and equipment from overloads and short circuits. The size of the overcurrent protection devices should be based on the ampacity of the conductors and the rating of the equipment being protected. Fifthly, conductor sizing is important to ensure that the conductors can safely carry the expected load current without overheating. The conductor size should be based on the ampacity of the conductors, the ambient temperature, and any applicable dirting factors. Sixthly, voltage drop should be minimized to ensure that equipment receives adequate voltage. Voltage drop can be caused by long conductor runs, undersized conductors, or excessive load current. The NEC provides guidelines for calculating voltage drop and recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Seventhly, harmonic distortion can be a concern in systems with nonlinear loads, such as electronic devices and variable frequency drives. Harmonic currents can cause overheating of transformers and conductors, as well as interference with sensitive electronic equipment. Harmonic filters can be used to reduce harmonic distortion. Eighthly, surge protection should be provided to protect equipment from voltage surges caused by lightning or switching transients. Surge protective devices, or SPDs, should be installed at the service entrance and at critical equipment locations. Ninthly, regular maintenance and inspection are essential to ensure the continued safe and efficient operation of the system. Maintenance should include checking connections for tightness, inspecting conductors for damage, and testing overcurrent protection devices. Tenthly, documentation is important for troubleshooting and future reference. A complete set of drawings, including single-line diagrams and panel schedules, should be maintained and updated as needed. When addressing the specific scenario of a 400 amp, 120/240 volt delta high-leg system feeding a 200 amp panel with an air conditioning unit and other loads, the following steps can be taken to reduce the high-leg voltage. Firstly, measure the voltage on each phase at the 200 amp panel to determine the extent of the voltage imbalance. Secondly, identify the loads connected to each phase and calculate the current draw of each load. Thirdly, determine if the air conditioning unit is connected to the high leg, and if so, consider moving it to one of the other phases. Fourthly, redistribute the other loads as evenly as possible across the three phases to balance the current flow. Fifthly, verify that the neutral conductor is properly sized and connected to handle the unbalanced current. Sixthly, consider using a buck-boost transformer to reduce the voltage in the high leg if the voltage imbalance cannot be corrected by load balancing. Seventhly, consult with a qualified electrician to ensure that all work is performed in accordance with applicable codes and standards. Understanding the properties of a delta high-leg system is important. The delta connection is a three-phase electrical power system where the three phases are connected in a closed loop, resembling the Greek letter delta. In a 120/240 volt delta system, two of the phases provide 120 volts to neutral, while the third phase, known as the high leg, provides approximately 208 volts to neutral. The high leg is created by center tapping one of the transformer windings. This center tap provides the neutral connection for the system. The voltage from the high leg to neutral is equal to the square root of 3, or approximately 1/732 times the voltage from the other two phases to neutral. The high leg is often used to supply three-phase power to motors and other equipment. However, it is important to note that single-phase load should not be connected between the high leg and neutral, as this can result in excessive voltage and damage to the equipment. Balancing the load across the three phases is essential to prevent voltage imbalances and overheating. Single-phase loads should be distributed as evenly as possible to minimize current flow in the neutral conductor. Grounding the system is critical for safety. The system should be properly grounded to provide a low impedance path for fault currents, reducing the risk of electrical shock. The grounding electrode conductor should be sized according to the NEC and connected to a grounding electrode system. Overcurrent protection devices such as circuit breakers and fuses should be properly sized and installed to protect the wiring and equipment from overloads and short circuits. The size of the overcurrent protection devices should be based on the ampacity of the conductors and the rating of the equipment being protected. Conductor sizing is important to ensure that the conductors can safely carry the expected load current without overheating. The conductor size should be based on the ampacity of the conductors, the ambient temperature, and any applicable derating factors. Voltage drop should be minimized to ensure that equipment receives adequate voltage. Voltage drop can be caused by long conductor runs, undersized conductors, or excessive load current. The NEC provides guidelines for calculating voltage drop and recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. When troubleshooting a high-leg system, the following steps can be taken. Firstly, measure the voltage on each phase to determine the extent of the voltage imbalance. Secondly, check the grounding system to ensure that it is properly installed and functioning correctly. Thirdly, inspect the wiring for any loose connections, damaged insulation, or other problems. Fourthly, verify that the overcurrent protection devices are properly sized and installed. Fifthly, identify any unbalanced loads and redistribute them as evenly as possible across the three phases. Sixthly, consider using a buck-boost transformer to reduce the voltage on the high leg if the voltage imbalance cannot be corrected by load balancing. Seventhly, consult with a qualified electrician to ensure that all work is performed in accordance with applicable codes and standards. Remember to always energize the circuit before working on any electrical equipment and use insulated tools and wear appropriate personal protective equipment.